Well, this video is for Math 112, trigonometry, and this assignment, we won't have a quiz on this, but it does lead into the second project, and I think it's a really interesting topic, and it's about applying the ideas that we talked about in Chapter 2 about graphing to physical situations, because there are a lot of things in the world, whether they be machines or processes in the natural world that occur periodically. And these sines and cosines really lend themselves well to that type of function. So just very quickly, one of my favorite applications, I'm not sure if I did this in an earlier video or not because I love to talk about it, is the length of day function. Okay, I think we all know that the length of day is periodic, and we get longer days in the summertime and shorter days in the wintertime. However, the way that happens is in what in mathematics we call nonlinear. Okay, so let's say if we were to put January 1st here, we could change that to, make this a little bit different. But let's just say we put the start of the year at the origin here. That means that the shortest day of the year will be back here on December 21st. And just for simplicity's sake, let's say that's 8.5 hours. Okay. And then over here somewhere we have the midline value. We'll call this March 21st. And then we've got the longest day on June 21st. Another equinox on September 21st. And then that brings us back to the minimum, which is going to happen in the following December. Okay. So if we're down here at 8.5 hours, our midline value is a 12-hour day, and that'll happen on the two equinoxes. The longest day, let's see, if this is 8.5, so this is 3.5 hours different, so let's say this is going to be 15.5. We could get actual values for those and make this a little bit more accurate, but this is just kind of a quick sketch of this idea. What I find really interesting about this is that if you look at the slope of the curve, which is what calculus is all about, the slope of the curve is biggest right around the equinoxes. Okay? That means you're gaining the most daylight right around the March equinox and kind of 3 weeks on either side. Same thing, we're losing the most daylight in September. Once we get to December, we've lost all of that daylight already, and we just get this month right around the solstice where it's just dark well, not all the time, but it seems like all the time. Okay, so there's an example of a periodic function. I recently saw a presentation by a professor down at OIT, Oregon Tech, who teaches mechanical engineering. And in machines, you have a lot of things that are spinning around and driving other parts of the machine, and that creates angles and trigonometry. And that was a pretty interesting presentation as well. So just so for our purposes, I'm going to go over two problems here. They're going to be similar to the problems that you'll see on your second project. So let's first talk about the basics of graphing here. Let's see, so trigonometric graphs. So we could have A sine bx plus c plus d, or minus d. And we can also think of this when we're setting this up. Let's see, I don't want to call that c. What should I call it? I'll call that s for the shifted starting position. or we can use a cosine. A cosine bx plus c plus d. Or, again, we can set it up with the b factored out and then our new shifted starting position, just put it here. C is just going to be s times b, whatever that number happens to be. The reason why I put this format in here is because these are numbers that are going to come out of the situation. If you want to write it like this, you'll have to calculate C based on the values of S and B. Okay? All right. So remember, A is the amplitude, D is the vertical shift, B sets the period for the graph, and so on. Let's see here. What was it I was going to say? Oh, right. So if you go back into chapter 2 and if you look through there, you'll see there's a point where I say that A, the amplitude, is the half of the difference between the max and min values. Max minus min divided by 2. And D is the average, or half the sum, of the maximum and minimum values. Okay? All right, so those are really helpful if you've got maximum and minimum values and you need to calculate A and D. All right? And then, of course, B is equal to 2 pi divided by the period, because the period is 2 pi divided by B. And then the S value is going to be wherever we choose our starting position. And so I'll talk more about that in just one second. Let's look at problem 1 here. We've got a cross-section of a mountain that looks something like this. This is a little lake or pond. And then you've got a mountain coming up like this. That maximum height there is 150, and the depth of the lake is 50 meters. Let's see, that maximum value happens at x equals 400, and this minimum value here happens at x equals negative 200. Okay, so let's see, I think we've got enough information on here to get started. So we know the maximum y value is 150, positive 150, and the minimum y value is negative 50. So that says that our amplitude here is going to be half of the difference. Now be careful when you're calculating with negative numbers, because this is going to be 150 minus negative 50. What we're interested in is this distance right here. That's 150, that's another 50, that's going to make a distance of 200. And so that's going to make our A equal to 100. Okay? The midline value is going to be the average of these two values. And again, this minus comes with this formula. This minus comes from the value of the minimum. Okay? Similar thing's going to happen here. We're going to have 150 plus negative 50. And so that's going to be 100 over 2, which is 50. And so that's going to be the midline value. So notice that the midline value, this is not the midline value right here. So you can't start a sine function at 0, 0, because that's not the midline value. That's happening up here at 50. Okay? So that's the actual midline value. And you can see it goes up 100 to the maximum, and it goes down 100 to the minimum. All right, so we've got a value for A, we've got a value for D. Now, a couple things. We need to choose either a sine or a cosine function. We can actually use either one on this. And then, once we do that, we need to figure out the period and our new starting position. So the starting position, and whether you're using sine or cosine, are really closely related to each other, okay? So if I were to choose a starting position up here, okay, then this would be a cosine function, because we're starting at the maximum, right? So that would give us a positive cosine function. If we wanted to start down here at the minimum, we could use a negative cosine function. That's entirely your choice. They're both correct. Okay? Starting a sine function is tricky because we don't really know what the x coordinate for this position is. We could dig into it a little bit. I'm going to use a positive cosine graph, and this is going to be my new starting position at x equals 400. So let's do that. Let's say y equals, let's see, a is 100, positive cosine. I'll just put the b in there now, and then let's see here. Oh, I need to change the sign on this. I suppose I should call this x minus s. If I really wanted to be accurate about that. Because here we're going to have x minus 400 and then plus 50. Because remember, we set this equal to 0, and the solution is our new starting point. So if we set x minus 400 equal to 0, then that means x equals 400 is the starting point for our positive cosine graph. Okay. Now, this b, the value of b, is the last thing that we don't quite have yet. As it turns out, I think this actually is one full period of the graph, but I only know that because I found it out from a different method. What I'm saying is don't rely on the picture and assume that this is one complete period. Okay? What we can look at here is this from the minimum to the maximum. That is 1/2 the period, and that is equal to 200, and 400 equals 600. So that means our period is 1200, and b is 2 pi over 1200, which is pi over 600. So now we can fill this in. This is 100 cosine of pi over 600, and then x minus 400, and then plus 50. Okay, so that's the first part. Write an equation expressing y in terms of x for the points along the surface of the mountain there. Okay, now we get to the interesting part of the question, which is that there is this treasure located where x is 130 and y is 40. So again, it's not on the surface, it's been buried. And the question asks, is it shorter to dig a horizontal tunnel, or is it shorter to dig a vertical tunnel? And again, I would impress on you the importance of not just looking at the picture and saying, well, it's shorter on the horizontal end. That may be true, but it may not be true. Okay? So let's calculate which of those tunnels is longer and which one is shorter. All right, let's see here. Now let's erase most of what we've got here. Now that we've got our function, we don't really need most of this. And if you need to see it again, you can always back the video. All right, so let me rewrite this over here. Y equals 100 cosine pi over 600 x minus 400 plus 50. Okay, and if you wanted to write this in the other format, right, then you could just write pi over 600 times x minus 2 pi over 3, and then plus 50. Okay, let's see here. Now, what we need to know is the coordinates for this point right here and the coordinates for that point right there. Let's see here. So this is where x equals 130. So let's see here. So if I wanted to calculate that y value, where x is 130, do 130 minus 400 plus 50. Okay, let's see here. Now again, in these situations, we want to make sure that we're working in radians and not working in degrees, okay? So that's the first thing I'm going to do, is I'm going to change my calculator to be in radians rather than degrees. And then I'm going to calculate the cosine of this expression right here. 130 minus 400, negative 270 times pi over 600. And so then I've got a nice irrational number here of radians that I'm going to take the cosine of. And again, I'm rounding it off to write it down, but it's sitting right here on the calculator. There's no reason to round it off when I calculate cosine and then I hit second negative sign to get that answer. That's not been rounded off. There we go, there's that. And then times 100. So 100 times, what was that? 0.1564. And then plus 50. I don't know why I wrote 500 there. There we go. So that's going to be what, 65.64? Okay. 65.64. So what that says is this point right here is the point where x is 130 and y is 65.64, which says that if you dig a vertical tunnel down to where the treasure is hidden, then that vertical tunnel should be a distance of 25.64 meters. We're working in meters here. Okay, good to know. Now let's see here. We need to calculate the horizontal one. So let's see what that looks like. This is the vertical one. So the horizontal one is where y is equal to 40. So we'll put that in for y. Got our cosine pi over 600, x minus 400 plus 50. Okay, so this is a little bit trickier. Let's see, we're going to subtract 50 on both sides. This will be negative 10. And then divide on both sides by 100. So this is going to be negative 0.1 for the cosine. And now we need to take an inverse cosine on both sides. So let's see here. Make sure you're in radians. Second cosine is the inverse cosine, negative 0.1. Okay. And so that's going to be, let's see here, we'll call it 671. And that's going to be pi over 600 times x minus 400. Okay, let's see here. So, 0.671. So I'm going to multiply that by 600 over pi, and then add 400 to it. And again, I've rounded it off to write it down. The full value is right there. There's no reason to replace it with a less accurate number. And I'm just going to multiply by 600 over pi, which will be about 319.13. Let's see here. Okay. So this is kind of interesting. Add 400 to this, and you can see x is going to be 719.13. Well, that's out here somewhere. Okay? That's actually this intersection that I found. So let's see here. There are a variety of ways to get around this, and I'll actually talk about this, those last two sections in Chapter 3. is where we talk about this issue where you've got multiple solutions. So I was debating about doing this before I started the solution. So what I'm going to do here is I'm going to do solution by graphing. Okay. So let me get the graph typed in here. Let me come over so you can see what I'm doing. Okay. So there's the calculator. There we go. And so we want to graph our original function. 100 cosine and then pi over 600. Let's see here. And then x minus 400, close parentheses, plus 50. Okay. And then I'll just hit graph, but this is not the window we're going to want. Okay, this is from -10 to +10 on both the x and the y's. So what we need to do is we need to go in and change these so that they're more like what we're seeing in the picture, from 400 to 800, and our y's from -50 to 150. Okay, so there's a much better picture of what we're working with. And then to solve this by graphing, we go in and we graph a y equals, what was y? Y equals 40 on there. All right, so there's the line. So here's the solution we found algebraically out here. Now we're going to use the calculator to find this one. We can do it without the calculator. It's just we haven't talked about that yet. That's later in chapter 3. Okay, so to do this, we want to hit second trace. That brings up the calculate menu. You can see number 5 is the intersection. Okay. If you've only got 2 graphs on here, this first curve and second curve thing, you can just hit enter, enter, and enter one more time. And there's the intersection where x is 80.86. Yep. Okay. So let's see what we've got here. So this point right here now is 80.86 and the y is 40. So this is going to be just short of 50. Our horizontal tunnel is going to be 130 minus 80.86, and so that's going to be 49.14 meters. And so my warning that you not go by the picture and just say, well, that vertical one sure looks longer. It's not. It's basically half the distance. Okay, the horizontal tunnel is twice as long as the vertical tunnel. Okay, so your project will involve a problem not exactly the same as this, but it'll have similar ideas. Okay, you'll get information about the maximums and minimums. And also some information that allows you to determine what the period would be, and then we want to put that all together into making an equation. So I'm going to do one more example here before we stop. And then again, the second project I'll hand out towards the end of the month. It'll probably be, I think, the 24th or so, that week of the 24th anyway. I'll hand out the second project, and then that'll be due at the end of the term. Okay, so problem 2 here is a paddle wheel problem, and there's no diagram for this one. I'll draw one on the board here. So we've got water like this. We've got a paddle wheel, something like this, that's spinning, and this distance that we're talking about is this d right here. Okay, you'll have a maximum d here, and then you'll have a minimum d down here, where d will be negative because it's under the water. Okay, a point on the paddle blade moves in such a way its distance from the water is a sinusoidal function of time. So at t equals 4, the point was 16 feet above the water line, which is the maximum. Okay, that's important information. The diameter of the paddle wheel is 18 feet. So that says that if this D is 16 feet above the water, then that must be 2 feet, which would be the minimum value. D equals -2 will be the minimum value. Let's see, I don't think we know what time that's going to happen, but we could probably conclude that in just a minute here. And it completes a revolution every 10 seconds. Okay, so let's see here. So that says that our period then is 10 seconds, right? Because it'll go all the way around in 10 seconds. So if P is 10 seconds, that means our B value is going to be 2 pi divided by 10, or pi over 5. Okay, great. So we already know the value for B here. And if it's at the maximum at t equals 4, that means it'll be at the minimum after half the period, or 5 seconds later. That'll happen at t equals 9. Okay. Let's see here. So we can calculate A and D as well. Let's see. D, the midline value, is the average of the maximum and the minimum. So 16 plus -2. I guess I'm standing in the way there. So that'll be 14 over 2, which is 7. And then our amplitude will be the difference between these two, 16 minus -2, which is 18 over 2, or 9. Okay. So here we've got some information about the t value when the D is at a maximum. That says to me that we could use a cosine function, right? Because the cosine starts at the maximum, right? We could dig into this a little bit, and we could find out where the midline is and when it's going to be there. There's nothing wrong with doing that. We've got enough information about the period, right? Because you can chop the period in half. You can also chop it into 4 pieces the way we did when we were making those graphs. And that can give you information about where the midline values are going to fall and where exactly they are along here, right? If, let's see, if our amplitude is 9 and the midline is 7, well, then we can calculate when it's going to be there if we know that it takes 10 seconds to go all the way around and so forth. But anyway, I'm going to use a cosine function. Let's see, we've got a value for A, so y equals 9. That's a positive cosine function. We've got a value for B, pi over 5. And we've also got a value for our new starting position, right? Because at t equals 4, that's when it's at the maximum. So that'll be x minus 4 inside the parentheses. And our midline value is 7. And then it'll go up 9 to 16, and then it'll go down 9 to -2 on the minimum. Okay, so there's our function. Let's see, what questions are we being asked now that we know this? How far above the surface is the point when the stopwatch reads 5 seconds? Okay, so there are a variety of things that you can do here. We can just straight calculate this. With x equal to 5. You can type it into the graphing section, and you can use that to calculate values for you. I'll go ahead and do this on the calculating screen. So, first we're going to have, what is this, part B? So, and the y is D, okay? So this is going to be 9 cosine pi over 5, and then 5 minus 4 plus 7. So that's just the cosine of pi over 5 plus 7. Okay, so pi over 5, and then we want the cosine of pi over 5. And that's going to be 0.809. We'll multiply that by 9. And again, I'm going to round this off as I'm writing it down, but I'm going to leave the full value on the screen. And then when we multiply by 9, we get 7.28. And so the answer here is about 14 feet. 14 and a quarter, 14.28 feet. Okay. What about when x is 17 seconds? So this will be then 17 minus 4. So that'll be, right, pi over 5 times 13, so 13 pi over 5. All right, let's do some calculating here. Cosine 13 pi over 5. And what do we get there? Negative 0.309. So we'll multiply that by 9. Negative 2.78 plus 7. And so this is going to be what? About 4.22 feet above the water line. So let's see here. So when this is at t equals 4, we're at the maximum here. At t equals 5, we've come off the maximum a little bit, and we're down at 14 feet above the water. And then, let's see here. At t equals 9, we'll be down at the minimum. At t equals 14, we'll be up at the maximum. And then t equals 17, we'll be down here just 4 feet above the water line. Okay, so this is always a question for me when I teach this class because it follows so nicely on all the stuff that we've done about graphing, but we don't get to the second project until a little bit after this. So like I said, there's not going to be any quiz on this. You may just want to put this aside and wait till I give out the second project. That's fine. I'll probably do a separate video for the project where I talk about those problems specifically, but a lot of the detail about how to approach these problems is in this video, which I'll also put a link to when I post that second project. Oh, as always, if you have any questions, please let me know. Thanks.